All right, so this is your Learning Target 17, one of the last videos you'll get from me. I guess that's cause for celebration. It's Introduction to Organic Chemistry, where we're going to talk about alkanes today. And the goal of this particular learning target is to be able to name the first 10 fundamental alkanes and to be able to apply IUPAC rules to name straight change and branch change isomers of alkanes, and I also threw cycloalkanes in there as well. One of the best parts of this learning target, one of the best parts is I'm going to draw something like this. I'm making it up as I go. Throw chlorine in there. And you know what? You'll be able to name it. You'll be able to give me the name of the compound that I just modeled there with what we call a skeletal structure. I love having you do this at home in front of your family and friends, and they will have absolutely no clue what you're doing because the symbols look so strange. One of my favorite things to do. So what is an alkane? Alkane is defined as any hydrocarbon, only carbon and hydrogens with just single bonds. No double bonds, no triple bonds, and no other fundamental groups, which we will learn about a little bit later. Alkanes are named based on their length. On the next two slides, you're going to see some really important tables that I would highly suggest that you copy down, because those tables are going to give us prefixes that will indicate the size of the carbon chains we are using. So here's your chart of your first 10 hydrocarbons, their molecular formulas, boiling points, and melting points. I would say that the only three columns that are really important are the name, the number of carbons, molecular formula. I'd also pay attention to the fact that each one of these has a unique prefix, and the unique prefix is going to indicate the length of the carbon chain. So for example, meth means 1 carbon, eth means 2 carbons, prop 3, bute 4, pent 5, hex 6, hept 7, oct 8, non 9, and dec 10. You're going to see here that the formula for each of these alkanes follows the equation C sub n H2n plus 2. So where n is going to be the number of carbons in the chain, and if I double the number of carbons in the chain and add 2 to that, I'll get the molecular formula for that particular alkane. The longer the chain, the higher the melting points, boiling points, because there are more intermolecular forces to pull apart, and when you have to put more energy into a substance in order to get it to change from a solid to a liquid, the melting point increases. Longer the chain, higher melting, higher boiling point. And as I said before, the N in front means the number of carbons, but also the N in front here, in front of each of these, means that those alkanes have no branches. They are just straight alkanes where you're just going to have the line of carbons across the page. So I take a moment here, make sure you get at least the first three columns written down, or have bookmarked this that you can get back to it. Here is another chart that's basically the same as the first chart, but instead of giving me the names of the alkanes, it's going to just give me the prefixes that indicate the length of the carbon chain. So these are your prefixes again: meth, eth, prop, bute, pent, hex, hept, oct, non, dec, goes 1 through 10. Have those written down as well, or just underline them on the previous chart that you copied down. Those are really important to know. Okay, this is one of my favorite things to teach. We're going to learn how to use skeletal structures to draw alkanes. The beauty of skeletal structures is that you don't represent the hydrogens at all because you just assume you have so many of them that they just fill in the blank gaps. And that the endpoints of a straight line represents 2 carbons. If there's a break in the line, that's where 1 additional carbon is added to the chain. So let's first start with propane. And here's the molecular formula for propane. Excuse me. But here is what we call the constitutional formula for propane, which shows us the placement of each of the carbons. So I can have CH3, CH2, CH3. Basically, using this constitutional way, I can tell the placement of each of the carbons and the hydrogens in the chain. Now to represent this using a skeletal diagram, I count my number of carbons, 1, 2, 3, and I can say 1 carbon, 2 carbons, 3 carbons. That is the skeletal diagram for propane. Notice I don't even represent the carbon or the hydrogens. The hydrogens are not drawn. Another way of drawing it is this exact same way, is an upside down V. And I can remind myself what this means. This would be a carbon with 3 hydrogens on it. This would be a carbon with 2 hydrogens on it. Remember, each carbon wants 4 bonds, and this would be a carbon with 3 hydrogens on it. So the skeletal structure, once again, does not indicate hydrogens, and the breaks in the line will tell you where the carbons are placed. So now we're going to get into isomers of alkanes. And the definition of an isomer is that it has the same number of carbons and hydrogens as another version of that particular molecule, but it's in a completely different arrangement. We find where those additional carbons have been put by indicating the additional carbons with a number. The numbers are put on what we call branches. And the numbers are assigned, and this is really important. The numbers are assigned so that we can number the carbon where the branch is on the lowest number. The size of the branch is represented by the prefixes that you learned on the previous slide, but the suffix is YL. And if there's more than one of the same size branch, numeric prefixes are used, such as mono, di, tri, tetra, so on and so forth. So here's an example here. This is going to have 4 carbons. I'm going to draw out the skeletal structure that goes with this, and then I'm going to show you how we use the skeletal structure in order to name it. So I'm going to first count all the carbons that are not in the parentheses. So 1, 2, 3. I'm going to draw the skeletal structure where the 3 carbons that I underlined are in the propane configuration, like you saw on the last slide. So this is going to be 1 carbon. That's going to be my 2nd carbon. That's going to be my 3rd carbon. And then on the 2nd carbon here, I end up having a CH3 group. So I draw a line just like this. So that is where the CH3 comes in. So now, kind of looks like I have almost a bird's foot going on. I can go ahead and name this particular structure. To name it, I want to find the lowest numbered branch where this CH3 group lives. So I can number it from left to right. I can go 1, 2, 3. And numbering it this way, I'd find that the CH3 group is on the 2nd carbon. Well, you know what? I could go this way too. 1, 2, 3. And it'd still be on the 2nd carbon. And since this molecule is symmetrical, I would notice that I could rotate this whole entire thing. If it rotates, it's not going to rotate for me. So since it didn't rotate, I'll just number it in a different fashion. I could even number it from the lower right-hand corner to the top, and I'd still have 3 carbons. 1, 2, 3. Regardless of which way I look at this, the branch is on the second carbon. So when I go to name this, I start with the longest main chain. The longest main chain is 3 carbons long. So I start with propane. And I've got a branch in the center with 1 carbon. 1 carbon is a methyl group, and it is on carbon 2. So I say 2-methyl propane. 2-methyl propane. So these kind of get, you have to kind of get used to naming these. You have to start looking at them like they're a puzzle, and you're going to try to number the carbon chain so that you have the longest chain possible. Here's another example one. So I've got this long constitutional name for this long alkane. I'm going to draw it out, and then I'm going to attempt to name it. So if I count here, the carbons that are not in the parentheses, I've got 1, 2, 3. So I got another propane again. So I can go 1, 2, 3. Then off the second carbon, I've got a branch of 2 carbons. So I go 1, 2. And then off the third unparenthesed carbon, I got another 2, 1, 2. So you'll notice that when I drew this, all of a sudden, my longest chain grew from 3 to a lot longer. And now I got to figure out where my longest chain is actually going to be. So I can number this way, and I can go 1, 2, 3, 4, 5. Okay, so that's 5 carbons. I could also go 1, 2, 3, 4, 5, 6. So I can notice that the longest chain I have in this particular molecule is going to be 6 carbons long. I could go the opposite way as well. 1, 2, 3, 4, 5, 6. But there's going to be a reason why I'm not going to go that direction, because the carbon that is not in the longest connected chain would not be on the lowest numbered carbon. So now I'm going to name this thing. Here is my longest chain. I put this one as 1, 2, 3, 4, 5, 6. 6 is hexane. So hexane is going to be my last part of this name. And on the 1, 2, 3rd carbon, I've got another methyl group. So again, this is going to take some getting used to, but it's going to be pretty easy as soon as you get the hang of it. I'm going to redraw this really quickly because I want to show you what happens if I've got more than one of a particular branch off this. So here's 1, 2, 3, 4, 5, 6, 7. I'm going to have a methyl group here. I'm going to have a methyl group here. If I name this thing, or if I find my longest carbon chain, I go 1, 2, 3, 4, 5, 6, 7. And I numbered it from left to right because my branches will be on the lowest number at that point. And they're both methyls. And since they're both methyls, I can say 2, 4, di. Di means I've got 2 of these methyl groups, methyl, and then I've got a heptane because that's my longest chain. So that was 2 examples in one there. So now let's go the opposite direction. Let's take a name and make it into a formula and do the skeletal structure in between. So we work backwards on these. And when we work backwards, we are going to look at the longest carbon chain, which is always listed last. And it is heptane. So I'm going to go 1, 2, 3, 4, 5, 6, 7. And then it says that on the second carbon, there's a methyl. And on the third carbon, there's an ethyl. Now this is going to do something interesting. 1, 2. So when I do that, I now have 1, 2, 3, 4, 5, 6, 7. I've kind of changed the chain a little bit. There's actually 2 correct ways of naming this thing. The first correct way is exactly how I put it. And the second correct way is, if you notice on the third carbon here, 1, 2, 3, you got this branch looking thing. And when you've got a branch of 3 and the branch is connected to the middle carbon, this is called an isopropyl group, like isopropyl alcohol. So I could also name this thing 3-isopropyl, and it'd still be a 1, 2, 3, 4, 5, 6, 7 heptane. But in order to draw this, what I would do now is just, sorry, not to draw this, but to write the formula, I would just start left to right, writing what would be attached to each one of these spots. So on the first carbon, the hydrogens are not listed, but you have to have 3 of them to make 4 bonds. Every carbon wants 4 bonds. This one would have 2 carbons. This third one is going to be funny. This third one is going to have, instead of 2 carbons attached to it, it's going to have, well, it is also going to have 2 carbons attached. It's going to have a hydrogen, but then it's going to have this group here, which is going to be a CH3 group. This would be a CH3. This would be a CH. This would be a CH3 group. And then I would come here. Carbon 4 would be a CH2. Carbon 5, CH2. Carbon 6, CH2. And carbon 7, CH3. And that would be the way to write the formula for this particular alkane. Again, practice on these would be the way to get used to them. Okay, the last thing to talk about are cycloalkanes. So they are carbons that are bonded in a ring or a circle in some cases. And in order to name these, you put the prefix cyclo in the front, like cyclohexane that we've heard of before. They will have the formula CN, N being the number of carbons once again, and then you double that to get the number of hydrogens. You don't have that additional hydrogen attached to the end because it's ringed into itself to make 4 bonds. And for cycloalkanes, once you get to 6 carbons in a ring, those cyclohexanes stop being flat, and in fact, they end up being kind of like a saddle, and I will show you what that means in a second. So here is my formula for cyclohexane. And to draw the skeletal structure, you draw a hexagon. So that is going to be your cyclohexane. It's misleading, however, because it is not flat. And if you could draw your attention to the webcam that's going to be in the bottom right here. Put it on the screen. You'll notice that when I built this in a model, it is not flat. In fact, I've got one up in the air just like this. And these bonds constantly move. So those are rotating around each other, just like that. So that's my brief introduction to a cyclohexane. If I was to do something smaller, like a cyclopentane, this is kind of fun to draw. Cyclopentane, not cyclopentane, I want cyclopropane is what I want. Cyclopropane, 3 carbons, is a triangle. Cyclobutane, pretty fun, it's a square. So now we can use our geometry to represent different hydrocarbons. So you're going to see attached to this learning target a worksheet. Now, if you're in class with me, I have made photocopies because these are a lot easier to write in person, or you can open up your copy on Cami and write with a stylus, whatever you prefer. But we're going to practice some of those together, and thank you for paying attention.